We engineer highly optimized therapeutic proteins to treat complex diseases, yet a significant number of these biologics fails standard freeze-thaw stress tests during development. Regulatory bodies, like the FDA, mandate early freeze-thaw studies because unpredictable protein aggregation, where molecules clump together and lose efficacy, can derail a drug candidate's progress. When a biologic freezes, research usually identifies a few established physical stresses: the formation of ice crystals, cold-induced unfolding, shifts in pH, and cryoconcentration. But these factors overlook a significant variable. The liquid formulations are typically saturated with dissolved air. During freezing, this gas is forced out of the solution, creating temporary air-water interfaces inside the frozen vial. As the ice lattice forms, the expelled dissolved air generates microbubbles, creating up to 10 square meters of new interfacial surface area per liter. In this environment, protein molecules reorient their hydrophobic regions toward the air and nature. This raises a specific engineering question. If we alter the freeze-thaw cycle to physically extract this dissolved gas before freezing begins, can we preserve the protein's structural stability? A study by researchers Nosman and Dow sets out to test this hypothesis. The researchers selected human serum albumin, or HSA, as their model protein. HSA provides an ideal baseline because its sensitivity to air-water interfaces is well documented. The core experimental strategy relies on pre-freeze deaeration. By placing the liquid formulation under a 4 kilopascal vacuum for 15 minutes, the team can physically extract the dissolved gas. To isolate the effects, they established a matrix of treatment groups: untreated samples to serve as a baseline, deaerated samples, and deaerated filtered samples, which add a secondary membrane filtration step. They also introduced a secondary engineering variable, testing standard atmospheric thawing against reduced pressure vacuum thawing to observe how gas re-enters the system when the ice melts. To determine if this pre-freezing treatment protects the HSA protein, the researchers must first demonstrate that they can control and observe the microbubbles forming inside the ice. Before introducing the protein, the team measured dissolved oxygen to gauge total dissolved air, testing standard excipient solutions at various concentrations of between 80 and trehalose. In these charts, dissolved oxygen in untreated references hovers around 85%. After deaeration, the red and blue lines drop to 20%, regardless of excipient concentration. To determine if this drop translates into fewer trapped microbubbles, the team utilized a vertical freezing microscopy setup. In panel C, the densely packed left column shows the untreated reference, while the deaerated sample on the right is sparser, containing only 18% of the reference's bubble area. A schematic breakdown shows a distinct vertical gradient. As the ice moves upward, the remaining bubbles accumulate strictly at the top liquid air boundary. By extracting the dissolved gas beforehand, the researchers successfully eliminated nearly 80% of the air-water interfacial surface area from the frozen matrix. During this preparation phase, the researchers discovered a critical roadblock. The physical act of stirring the solution under a vacuum can introduce mechanical contamination. This chart shows the count rates from dynamic light scattering analysis. When standard glass stir bars were used during the deaeration process, the red bars indicate a spike, with scattering signals frequently exceeding 10,000 kilocounts per second. To understand these spikes, the team analyzed the solutions using microflow imaging. The imaging revealed that the glass stir bars were shedding thousands of microscopic solid fragments into the liquid. Here is the direct visual confirmation. The microflow imaging captures jagged, sharp-edged particles generated by the glass stir bars on the left. On the right, solutions stirred with PTFE bars show only a few sparse, rounded shapes, significantly reducing particulate contamination. However, even with the PTFE stir bars, the mechanical agitation left tiny nanoscale air bubbles suspended in the solution that did not have enough buoyancy to escape during the 15-minute vacuum treatment. To clear these remaining nanobubbles, the team implemented a secondary filtration step, pushing the liquid through a 0.2 micrometer membrane immediately following the deaeration. This established the finalized deaerated filtered, or DF, protocol, eliminating both the glass fragments and suspended nanobubbles. This ensures the results reflect the impact of freeze-thaw stress on the protein itself. With a clean baseline established, the researchers introduced the human serum albumin. Samples were then subjected to 1, 3, and 5 freeze-thaw cycles at -80°C. They initially measured structural integrity using size exclusion chromatography to assess soluble monomer retention. The resulting chromatograms show near-identical, overlapping peaks for all cycles. Across every group, the data indicates HSA maintained over 94% of its monomer integrity. Relying on this data alone can be problematic. Size exclusion chromatography lacks the sensitivity to detect insoluble, subvisible aggregates, obscuring the formulation's actual stability. Microflow imaging exposed a different reality. This chart tracking subvisible particles shows that the untreated samples experienced progressive aggregation. The particle counts jumped from around 1,000 in the reference samples to over 6,000 particles per milliliter by the 5th cycle. In contrast, the samples processed with the deaerated filtered protocol maintained particle counts near their pre-frozen baselines throughout repeated cycling. The removal of the dissolved air protected the protein. Relying strictly on monomer retention obscures localized damage. These findings prove managing dissolved air prevents subvisible particulate formation. Even with protective filtration, data revealed a slight upward trend in particle formation for treated samples. This prompted the researchers to investigate why aggregation was still increasing marginally. As this graph illustrates, the vulnerability occurs during the thawing phase. As the ice melts during standard atmospheric thawing, the headspace air inside the vial dissolves back into the liquid, restoring dissolved gas levels before the next freezing cycle begins. By thawing the vials under a 10 kilopascal vacuum, the researchers prevented this gas exchange. This approach locks in the deaerated state. The vacuum thaw line stays flat, maintaining the low dissolved oxygen levels and limiting aggregate formation across all 5 cycles. Researchers then tested these conditions against different dynamics, comparing standard -80° freezing to liquid nitrogen snap freezing at -196°C. Rapid liquid nitrogen cooling produces a fine ice matrix, subjecting proteins to intense stress. In this heat map, -80° samples show tight clusters. But under liquid nitrogen, the aggregates become highly dispersed and elongated, spilling completely down into the lower quadrants. Yet, even under the mechanical stress of liquid nitrogen, the pre-freeze deaeration protocol cut total aggregation by more than half compared to the untreated samples. Freezing speed dictates the physical crush, but dissolved gas dictates interfacial stress. Controlling this gas mitigates damage regardless of the rapid cooling rate. Summarizing the primary mechanism, it challenges the long-held assumption that ice crystals alone cause cryopreservation failure and highlights the role of in situ microbubbles. The protocol does have limits. Deaeration does not stop cryoconcentration, nor does it prevent the proteins from interacting with the solid ice-water interfaces. A baseline level of stress remains inherent to the freezing process. However, contrasting a standard formulation workflow with this optimized approach shows a clear structural advantage. A standard air-saturated liquid generates bubbles and subsequent aggregation. The holistic workflow isolates and neutralizes that variable almost entirely. Achieving this requires a two-pronged approach. Pre-freeze deaeration reduces the initial gas burden, but vacuum thawing is necessary to prevent air from redissolving during multi-cycle validations. Applying these methods offers a potential strategy for stabilizing protein candidates that show persistent aggregation during early-stage stress testing. Biologic stability involves managing the dissolved air ecosystem throughout the entire cold chain lifecycle, treating the gas-liquid interface as an engineered variable rather than an inevitability.